Hello and welcome to another tutorial. In this tutorial, I'm going to continue the discussion on the bisection method for finding the roots, the real roots of a real function. And to recap, we said that in the basic bisection method, we take the interval a and b, which is the interval that we are looking for roots inside that, and where the assumption is that the function is continuous over that interval. And then the basic binary search was to start with the midpoint, basically break the interval into two halves that have the same length, and then search for the root in each of them, and then we have two paths and we go down the paths until we find the root, right? But then we said that this process can be accelerated, at least in the beginning, if we add an initial guess for the root, because instead of dividing the initial interval into two halves with the same length, if the roots is around here and we set the initial guess here, and so then we can divide the interval into two halves. One has a smaller length and is closer to the root, so that can accelerate the convergence to the root. It doesn't really change that much the order of the error and the number of steps. It probably changes the number of steps a little bit, reduce it, if we have a good guess for the root, good initial guess for the root. Okay, so let's head to Eclipse and try to implement this. So we have our demo roots projects, and we have the real root function, which enforces a real function with a real argument, and then we pass this to the real root object that finds the root, and we already implemented the bisection method. I'm just removing these commented parts. We already implemented the bisection method start and end, and it already divides the interval into two halves with equal length. We have the stop conditions, and then we have the actual binary search, and if the binary search fails, we return a NaN, or not a number. If you recall, we also implemented a bisection which returns a list of roots, so finds all the roots, all the real roots over the interval, and based on how many times it divides the interval into subintervals, so how many initial subintervals it looks for. So what I'm going to do, I'm going to modify this bisection to add an initial guess. So let's copy this and then add the double guess, and I'm going to remove this. So that's pretty much it. Believe it or not, this works exactly what we wanted. So this is the bisection method with the initial guess. And if you probably can guess what I'm doing here. I'm using method overloading, which is a powerful technique, method overloading technique. And this method takes an additional guess, and I basically, so the stop conditions are basically the same, but this guess is just half of the start plus end, right? If the length of the interval is small enough, then we just call the midpoint as the approximation. Other than that, I do the binary search, and here basically this guess is the initial guess. So if the start and initial guess is less than 0, it means the root is here, and we call the bisection, which is the other bisection method, which is this method, right? It already computes the guess as the midpoint. So the only thing that we're changing here is that addition of the initial guess causes that the initial breakdown to be uneven, right? So the initial breakdown is start to initial guess and guess to the end. It's not a midpoint. So let's go and try to test this. Test 3. public static void test4, and I'm going to run test4. We're going to do the same thing here as the first one. X squared minus 2, and func, let's call this func x times x, and we're searching for 0 and 3 with the initial guess of let's say 1. Okay, now the problem here is that if I put an integer here, it goes and calls this method, which takes an integer and it returns a list, and that list is not a double value. So that's why the compiler is complaining. It's saying that I'm invoking that method, but it returns a list, the method that also takes an extra integer, but it returns a list, but I cannot convert it to a double. So you have to make sure that you're putting a double value here. So this means that run the bisection on this function over the 0 to 3 interval, but the initial guess is 1. So it goes initially, it goes into, instead of searching for 1.5 to 3, it goes and searches for 1 to 3. So in this case, it's not that it actually a little bit less improvement, but it still works. But if I set the, let's say I don't know, it's like 2.0, so it's a double value. So it looks for 0 to 2 and 2 to 3, and the root is 1.4, so it goes into the 0 and 2. 1.4. So if I said 1.3 or 1.5 even, then this is not different from the bisection method. So if I put 1, let's say 1.3, then one of the roots is very close to this interval, so it goes into 1.3 and 3. All right, so this is one thing. Another thing that we can do, which is much more interesting, is that trisection method, exactly like bisection, but we can accelerate it much more. So the way we accelerate it more is, instead of dividing into 2 halves, we divide it into 3 halves, and then run the bisection, or run the recursion. So we're still doing a recursive trisection. It's a recursive method, but exactly like the bisection, but we just divide into 3 halves. And as you can see, the number of steps ends up being log 3, not log 2. So that could significantly reduce the number of iterations. And the other things are the same. So the error is basically the initial length divided by 3 to the power of n instead of 2 to the power of n. As you can see, let's say n is 4, then 3 to the 4 is 81, 2 to the 4 is 16, so 1680, so it's a factor of 5. So this could have huge improvement in terms of the speed. So, and it's very easy and very similar in terms of implementation. It's very similar to the so I'm going to, implementation is similar to bisection, and we're going to use recursion again. Okay, so we're going to implement it exactly like bisection using a recursion. The stop conditions are the same, but this could have much faster convergence. All right, let's go to Eclipse. In the real root object, I'm going to here copy this. After this, I'm going to create a trisection method over the interval. Right now we don't have any initial guess, doesn't matter, but then we have to divide into 3 3 intervals. So I'm going to create a variable called delta, which is end minus start divided by 3. Instead of 2 we have 3, and then I'm going to have 2 guesses, right? Guess 1 is start plus delta, and then guess 2 is start plus 2 delta, or end minus delta. All right, and then here, if the start value is the root, we return start. If the end value is the root, we return end. If the length of the interval is small, then we're going to return the midpoint, start plus end. Okay, and then we're going to do a ternary search instead of binary search, and we check for the start and guess 1. If it's negative, we go into a start and guess 1 and call the trisection. Otherwise, we check for guess 1 and guess 2. If it's negative, we go into guess 1 and guess 2. And finally, we check for guess 2 and end. If it's negative, we go into check guess 2 and end. And remember, these are trisection, so we do a recursion on the trisection. We could in fact do a binary search again, but let's just go trisection. Okay, if all 3 ternary searches are failed, then we just return a NaN. All right, let's go here and do a public static, or maybe just copy and paste this one. Test 5. I'm going to run test 5. I don't have an initial guess, and instead of calling the binary search, I'm going to call the trisection. Instead of bisection, I'm going to call, and this should be much faster. Yeah, and we can also improve this, go from 3 divisions to 4 divisions, 4 sub intervals, which makes it much faster. But as you can see, even the dividing into 3 becomes a much faster algorithm. Okay, and similarly, we can modify the bisection that returns all the roots and do a trisection that returns all the roots. And we have these, instead of calling the bisection, we call trisection, and that's it. So you see, the beauty of improving this and writing recursively is that everything is the same, you just change the name. All right, so I'm going to use this one, but call it test 6. And in test 6, I'm going to call the trisection method. And let's run this. As you can see, we again have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 roots. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. And let's double check the root. 0, 146, 184, 211, 234. So we have 10 roots, 2, 4, 6, 2, 4, 6, 8, 9, 10 roots, and this also returns 10 roots. But compared to the bisection, the trisection is much faster. Okay. All right, so let's go back to our PowerPoints and do a recap, a quick recap. Again, so far what we have looked at in terms of the root finding algorithms were the ones that were based on the general lemma, and they only involved finding the value of the function, and no other information was checked or required. But after this, we're going to look at the methods that actually take advantage of the more information that the function has. What do I mean by that? I mean the slope of the function, the tangent lines. For example, Newton's method is a method that also looks at the tangent line. It takes advantage of that, and it could in fact be faster, provide a faster convergence, and that goes into the category of general gradient methods. Even for optimization, it's not just for the roots, also for optimization. Using the slope of the function could provide faster methods, but the reliability may not be as good as the bisection or trisection. What I mean by that is you have to check for more things. In fact, you have to also check for the slope of the derivative of the function, because if it's zero, if the derivative is zero, then you're in the, for example, in Newton's method that we look at some point, you will stuck and the algorithm fails. So having taking advantage of more information in the function is useful in terms of faster convergence, but we need to add more and more check conditions to make sure that the algorithm is working and is not going into a death loop or fails quickly. So we have to check for more conditions. But so far we've looked into the trisection, which is a much more improvement over bisection, the number of iterations, and also finding all the roots based on the bisection or trisection, which provides a very convenient way of looking at all the roots. And we will look at other methods and try to add more codes for those methods too. Thank you for watching, and I'll see you in the next video.